Hello everyone, and welcome to Topic 3, which is about quantum theory and the electronic structure of the atom. No big deal, right? In Topic 2, we looked at the atom, and we started to look at the history of the atom, and more importantly, diving into the subatomic particles of protons, neutrons, and electrons. By the end of Topic 2, we had somewhat of a vague idea of what the atom looked like, but to be honest, this was all new territory. At the beginning of the 20th century, scientists barely knew that there were even subatomic particles, let alone what the atom looks like and how they're all arranged. In Topic 3, we're going to dive deeper into the electronic structure of the atom. In other words, the structure of what does the atom even look like? How does it behave? And these little things called electrons, protons, and neutrons, where are they at and how can you find them? I'm going to tell you right now that Topic 3 as a whole is definitely one of those topics that is going to stretch your brain, so make sure you're ready to go. Throughout this topic, I'm going to do my best to explain various experiments and various discoveries that we've made, but I've also hyperlinked in the notes, both PDF notes for the instructor as well as your student notes, that will take you to additional YouTube videos that I think do a very good job explaining some of these concepts in an easily understandable way, as well as they're short to watch. So I encourage you, after you've watched the videos that I've made, please make sure you watch those videos as well. They're very short and they're really going to help solidify some of these concepts. Because like I said, Topic 3 is extremely dense. What we cover in Topic 3 is considered to be the current view of the atom. And as you can probably guess, it's weird. So with that being said, let's get started with Section 1, which talks generally about energy and light. So first let's talk about energy. The actual definition of energy is the ability to do work or transfer heat. Now, work and heat are actually processes. They are two processes that matter can do. But if we were to sum up what energy is in layman's terms, energy makes things happen. If something wants to happen, if something wants to do something, it needs energy and it needs to be able to give or receive that energy. And so that's a definition, a basic definition of what energy is. We'll cover energy more in this course, but for right now, that's good enough. There's also different types of energies. There's all kinds. There's chemical energy. There's gravitational energy. There's all kinds of energy. But if you take all the different types of energies that can be in the world and in the universe, they really can boil down into two main umbrellas. And that is kinetic energy and potential energy. So for example, one of the types of energies that we'll actually talk about later on in Topic 12 is thermal energy. And when you think thermal energy, you think about heat. You think about energy that comes from things being warm. Well, what makes things feel warm or hot? It's the vibration of the particles. The faster they vibrate, the more it's going to feel like it's hot. And so the reason why thermal energy falls under the umbrella of kinetic energy is because kinetic energy is any energy that has to deal with motion of particles. On contrast, chemical potential energy is a type of energy. Think about a battery. A battery contains chemical potential energy. The battery has the potential to do things based on the chemical composition of the battery. This energy would fall under the umbrella of potential energy, because potential energy is energy due to potential, either based on arrangement of the particles and or position, however you want to think about it. And so all the types of energies in the world are going to fall under these two categories of kinetic and potential. Now, with the idea of energy, it's good to note that there is a law of conservation of energy, just like there's a law of conservation of matter. And law of conservation of energy states that energy, just like matter, is not created or destroyed. Instead, it's conserved by just transferring from one type to another. If I have $20 in my checking account and I transfer it to my savings account, have I gained any money? Have I created or destroyed any money? No, I still have $20. It's just the account that it's in has changed. And in the same way, energy acts the same. Finally, what's the unit that we measure energy in? Well, the main unit that we're going to see is the joule, which the joule is a capital J. But it is important to note that joule is actually a derived unit, meaning the joule is made up of smaller units. For example, the joule is actually a Newton times a meter. Now, a meter we're familiar with, that's length, but Newton might be new to you. Newton is actually the unit that we use for force, which is more of a physics term. And Newton is another derived unit. Newton actually can break down into a kilogram meter per second squared. So that's what a Newton is. And then don't forget that there's a meter there as well. So that's why we get the total units of a joule is a kilogram meter squared over second squared. That's a lot, right? And you're like, what the heck? What? That actually those are the units that make up the unit of energy. Rather than have to write that the whole time, that's why we just came up with a unit called the joule. And so energy is measured in joules. Now that'll actually come into play later on when we look at some calculations. But for right now, it's just good enough to know that we measure energy in joules. Okay, so here's the problem. Do a little review from topic 2. In topic 2, we started out with the discovery of the atom, thanks to John Dalton. And John Dalton essentially believed that the atom was just simply a sphere, and that it was indivisible. We quickly realized that that wasn't the case, and that there were these subatomic particles, and J.J. Thomson came up with a new model known as the plum pudding model, where these electrons would just stick in the atom in this positive paste. It then turned into the atom having some sort of nucleus, which we knew was positive because of the protons, and the electrons were somewhere outside the nucleus, kind of zooming around. But to be honest, that was all we knew. And as scientists, we tried to figure out, does the atom behave like models that we've seen before? For example, based on this discovery, scientists started to believe, hey, maybe the atom kind of acts like the planets in our solar system, where the nucleus would be like the sun and the electrons would be like the planets. And so what they tried to do is they tried to apply classical physics, meaning Newtonian physics, physics that explains laws of motion, planetary movement. We tried to take those physics laws and apply them to really, really, really tiny things such as the atom. Some other classical models that we try to use is the idea that energy is continuous. What that means is that the belief was all matter could absorb energy and release energy in continuous amounts. Think of like a flow of water. It could be any amount. It could absorb any amount of energy. It could release any amount of energy. These two models quickly were not working. Once we started looking at the behavior of the atom a little bit closer, we quickly realized that these models that worked for bigger things like planets and moving cars were not working for small things like the atom. And so the Newtonian laws at the macroscopic level were failing to describe the behavior of microscopic things such as atoms and electrons. And so scientists had to change the way they were thinking. They had to start looking at different ways to look and view matter. And so what they did is they started to look at the interactions between matter and light to gain a little bit more understanding. And so let's talk a little bit about light. Light is described as traveling in waves, much like the ripples in a pond. If you were to drop a pebble in water and you notice those ripples moving out, that was how light was typically or generally viewed as. And so light is described as a wave. Now, a little backstory, because this will come into play later. Back in classical physics world, okay, scientists believed that there were either particles or waves. So, what they believed is that whatever they were looking at falled into one of those two categories. There was no bleed over. It was one or the other, very black and white. And so at the time, light was considered to be over here in the wave category. Let's talk a little bit about light. Light is actually composed of two components, electric waves and magnetic waves. A light wave actually has both of those components, and that could be shown down here. So if you think about a wave, okay, think about like if I had a slinky, and I just went up and down, up and down. That's an example of a mechanical wave. And so this right here would kind of demonstrate a traditional mechanical wave. Well, a light wave actually has two components to it. Like I mentioned, it has the electric wave, which is shown here in red, going up and down. But then it also has a magnetic wave, which is shown in blue, oscillating perpendicular. This whole thing is a light wave. It's not that it's two waves, it's one wave, but it just has two parts, the electric and the magnetic, which is why light waves, or just simply light, is also synonymous with what we would call electromagnetic radiation. So you have electro and magnetic in the term to indicate that there's the two parts. So electromagnetic radiation or electromagnetic waves are made of those two properties. The speed of light, no matter what kind of light wave we're talking about, all light waves travel at the same speed, which we denote by the letter c, which means the speed of light, which is 2.998 times 10 to the 8th meters per second. Pretty darn fast. So continuing on with this idea that light is a wave, it's important to talk about the anatomy of a wave first before we talk about any calculations. So taking a look at a very simplistic wave down here, just so we can demonstrate the definitions. First of all, we need to be familiar with a wavelength. A wavelength is defined as the distance between two successive peaks, or what we would call as crests. So if I measured this point here to the next crest over, that is a wavelength. Notice the symbol we use for wavelength. It is the Greek symbol called lambda. It looks like an upside down Y. Now the SI unit for length, even if it's a wavelength, is meters. So remember, all length, according to the SI units, are meters. You're going to notice that because we're dealing with really tiny waves, it's not uncommon to see wavelength represented in nanometers. And so we'll have to convert that to meters. We'll look at how to do that when we start looking at an example. The other thing we need to be familiar with is this concept known as frequency. If I were to choose an arbitrary point along this line right here, let's say this point right here, and what I did is I timed, with my cool Apple Watch, I timed how many waves are going to travel through this point in 1 second. That would be the definition of frequency. Frequency is defined as the number of waves that pass a particular point per second. And so because we're counting how many waves per second, the units for frequency is 1 over second, which is the same thing as second to the negative first, which is the same thing as hertz. So oftentimes you'll see me use hertz, but no, it is the same thing as these two. And so we don't need to convert hertz to anything. It's already in the unit it needs to be. As far as the variable of what we use for frequency, we use the Greek symbol nu. It looks like the letter V, but technically it's the Greek symbol nu. And nu stands for frequency. Sometimes you'll see frequency as the letter F. We won't see it like that in this course, but if you ever look online at a different website, you might see that. So we actually can get the equation of the light. I call this the light equation. The speed of light can be calculated, or not calculated, but we can use the speed of light because we know what it is. The speed of light is equal to the product of wavelength times frequency. Wavelength, remember, has to be in meters. Frequency has to be in units of 1 over second. When you multiply those together, you end up getting the units of meters per second, which is what speed of light is measured in. You need to make sure that your units for wavelength and frequency are correct before you use this equation. One last thing in this video, notice the relationship between wavelength and frequency. Since the speed of light cannot change, it always has to be the value of the speed of light, then think about what happens if wavelength were to increase. Frequency would then have to decrease in order for the speed of light to remain the same. This is known as an inverse relationship. And it's important to know that these two units, wavelength and frequency, have an inverse relationship. We're going to continue on with section 1 in the next video, where we'll be talking and looking closely at the electromagnetic spectrum.